We live on a planet teeming with life. From the deepest ocean trenches to the highest mountain peaks, life is everywhere. It is complex, diverse, and beautiful. This reality leads us to a profound question. If life could happen here, could it happen elsewhere? We look up at a night sky filled with countless stars and wonder, are we alone? This question has many possible answers. The rare Earth hypothesis offers one of them. It suggests that while simple microbial life might be common throughout the cosmos, complex life, animals, plants, conscious beings like us, is exceptionally rare. This idea is not a statement of fact. It is a hypothesis, a reasoned proposal that challenges the assumption that a universe full of planets must also be full of complex life. It invites us to consider the long chain of events and specific conditions that allowed complex life to arise here. The story of a life-bearing planet begins with its star. Our sun is the anchor of our solar system, providing the light and energy necessary for life. But not all stars are created equal. The vast majority of stars in our galaxy are red dwarfs. They are small, cool, and incredibly long-lived. This might sound promising, but red dwarfs are known for violent flares that can strip atmospheres and sterilize close-in worlds. On the other end are brilliant blue stars, magnificent, but short-lived and furious, burning through fuel in mere millions of years, a blink compared to the billions complex life needed on Earth. Such stars likely die before complex organisms can arise. That leaves stars like our Sun, G-type main sequence, relatively stable and long-lived. For over 4 billion years, our Sun's output has been consistent enough for life to begin and evolve. Frequent stellar variability would drive chaotic climates that stall evolution. Location in the galaxy matters. The galactic center is crowded and irradiated. The outskirts are metal-poor with fewer rocky planets. We orbit in a quiet, stable, chemically rich galactic suburb. With the right star in the right neighborhood, you need a planet in the right place. This is the classic Goldilocks, or circumstellar habitable zone, where liquid water can persist. Too close, like Venus, and water boils into a thick atmosphere. Too far, like Mars, and water freezes out. Earth sits comfortably in the zone, with a nearly circular orbit that stabilizes climate. Highly eccentric orbits drive extreme heat and cold, hard on long-term habitability. Abundant liquid water is foundational. It dissolves, transports, regulates, and likely cradled life's origin. We find ice and vapor elsewhere, but stable, long-lived oceans may be rare. They require a precise balance of temperature, pressure, and geological activity. Earth's water was likely delivered by comets and asteroids during formation. A planet must be massive enough to hold water, but not so big it becomes a gas giant. Right orbit, right mass, right delivery of materials. A delicate balance that made our blue marble possible. A haven for life in the cold vacuum of space. A perfect orbit and water still aren't enough if geology is static. Earth is geologically active. Plate tectonics, drifting, colliding, sliding plates, may seem destructive, yet they underpin biosphere health. By cycling carbon through air, ocean, and crust, tectonics regulates climate over deep time. Volcanoes add CO2, warming the planet. Oceans and rocks lock it away, while subduction and volcanism keep the cycle running. Without recycling, CO2 could vanish into ice ages, or build to a Venus-like runaway. Earth's molten outer core powers a magnetic field extending into space, the magnetosphere. It shields us from solar wind that would strip atmospheres molecule by molecule. Mars cooled, lost its global field, and much of its atmosphere followed. The shield also deflects harmful radiation that would batter DNA at the surface. A living interior driving tectonics plus a strong magnetic field may be a rare, critical pairing. For complex life, a planet can't be a dead rock. It must be geologically alive. If these features are uncommon, that may help explain the Fermi Paradox. See our episode for more. The Moon, familiar, beautiful, may be indispensable. Unusually large for a rocky planet, our Moon strongly tugs Earth. It steadies Earth's axial tilt, sustaining predictable seasons. Without it, planetary tugs could swing tilt wildly, crashing climates. Complex life needs long-term environmental stability. The leading theory: a Mars-sized impact birthed our moon. A contingent accident, not guaranteed. Life uses carbon, hydrogen, nitrogen, oxygen, phosphorus, sulfur, plus vital trace elements. A world must form where these elements exist and incorporate them in the right proportions. Crust and mantle composition decide which nutrients reach the biosphere. Tectonics and volcanism continually resupply essential chemistry. Then, time. Simple life appears early, but complexity takes billions of years. Multicellular animals surged during the Cambrian, after 3 billion years of evolution. Evolution experiments through mutation, selection, adaptation, toward complex bodies and nervous systems. Across deep time, worlds face catastrophes that reset evolution. Earth suffered mass extinctions yet wasn't sterilized. Life recovered. Luck matters. A planet must navigate billions of risky years to reach animals and thinking beings. Each factor, the right star, the right orbit, geology, moon, chemistry, and the right amount of time, is one coin in a tall stack. Start with a stable G-type star in the galactic habitable zone, plus a rocky world on a near-circular path. Add sufficient mass to hold air and oceans. Add plate tectonics to regulate climate. Add a strong magnetic field for protection. Add a large moon for tilt stability. Then the right elements, no disruptive giants, and avoiding sterilizing supernova or impacts. Each coin lowers the odds. Missing one can topple everything. Rare Earth argues the stack for complexity is very tall, maybe rare. Multiply vast planet counts by tiny probabilities, and the final number could still be small, possibly 1. But humility matters. Our conclusions rest on a sample size of 1. Could life thrive around red dwarfs, shielded by thick air, global oceans, or in permanent twilight? Might other planetary configurations stabilize tilt, or other feedbacks regulate climate without tectonics? Could non-water solvents like methane or ammonia host life? Extremophiles widen our sense of the possible. The rare Earth hypothesis presents a sober case that our path to complexity could be vanishingly rare. The universe might teem with microbes, while complex ecosystems are few and far between. Forests, animals, thinking beings. It grounds us, reminding us of Earth's intricate, perhaps fragile balance. It's a powerful potential answer to the Fermi Paradox. Watch that episode for the broader puzzle. Not doom, motivation. With tools like JWST, we can analyze exoplanet atmospheres for biosignatures like oxygen and methane. We must disentangle geochemistry from biology with care. Focus the search on worlds meeting key rare Earth criteria. Testable, step by step. Answers won't come overnight. We'll probe Mars, Europa, and Enceladus. Finding microbes elsewhere would transform this hypothesis. Discovery forces revision. Silence lends rare Earth more weight. Each result adds to a cosmic puzzle. The story is still being written. Rare Earth is one chapter. It asks us to appreciate the long chain that led to this moment. What will our telescopes reveal next? Is the galaxy a desert or a garden with hidden oases? For the full picture, watch our episodes on the Great Filter and the Drake equation next.
Thank you for watching. Please subscribe to the Off the Chart Multimedia YouTube channel for more fascinating videos.